Welcome to EPG Pathshala lecture series in computer science. This course is on operating systems. This module will understand what is meant by page replacement algorithms and we learn a few page replacement algorithms. So, the learning objectives for this class is to understand page replacement, to learn how optimal page replacement algorithm works, to understand how least recently used page replacement algorithm works. So, what is page replacement? A process is divided into pages and a page that is currently being executed has to be kept in the main memory, or the currently executing instruction has to be placed in the main memory. And if the page is not present in the main memory, it has to be brought into the main memory. If a process has got say n number of pages, it is not necessary that all the n pages has to be present in the main memory. Only the page that is currently being executed needs to be present in the main memory. This is called demand paging. So, in demand paging, we bring in the page into memory only when it is needed. And when you are bringing the page into the main memory, you need to find out a free frame in the main memory, and in that particular place, in that free frame, you bring in the required page. But if there is no free frame in the main memory, then you need to choose one page one frame which is currently kept in the main memory, move that page outside to the secondary storage device and then bring in the required page into this particular page. So, you need to select a victim page which has to be moved out into the secondary storage device and then you bring in or swap in the required page. So, this is called page replacement, that is moving out one victim page outside and moving in the required page is called page replacement. And which page is chosen as the victim page? For that you have a number of algorithms and they are called the page replacement algorithms. And now we will understand what is meant by this optimal algorithm. In the earlier class, we learned about an algorithm called the first in first out page replacement algorithm. In FIFO algorithm, the page that was brought into the memory first is chosen for replacement, or the page that was brought in earlier is chosen for replacement. But the problem is that it suffers from an anomaly called Beladi's anomaly. So, we will understand an algorithm called the optimal algorithm in which the page that will not be used for the longest period of time in future will be chosen for replacement. And this algorithm has got the lowest page fault rate compared to the other algorithms, other page replacement algorithms, and this algorithm does not suffer from Beladi's anomaly. So, we will see how this algorithm works. Consider this reference string. This reference string is the sequence of references to different pages, and you have say there are three page frames in the memory. So, there are 3 frames in the memory, and with this reference string we will see how optimal page replacement works. So, the first reference is to page number 7. So, there is free frame in the main memory. So, 7 is brought into this free frame, and the next reference is to 0. So, 0 also has space in the memory. So, 0 is brought into the main memory. The next memory reference is to page 1, and page 1 can also be brought in because there is a free frame. And now the next reference is to page number 2. This page 2 is not present currently in the physical memory and hence it has to be brought into the physical memory, but you find that there is no free frame here. So, you need to choose one among these 3 to swap out so that you can bring in 2 inside. So, which one should be chosen? It should be one of these 3 which will not be used in the recent future or in the near future, or you need to choose a page which will not be used for the longest amount of time. So, you look into this reference string, you need to choose one among 0, 7, 0 and 1. 0, you see that it will be very soon it will be referred to. Then you see 1 will also refer to after that. Then after some time 7 will be referred to. So, you see that 7 is the frame or is the page that will not be referred to in the near future, or 7 is the page which will not be used in the near future. So, 7 is chosen for replacement and this page 2 is brought instead of 7, or 7 is moved out and 2 is brought into the main memory. And the next memory reference is for page 0. Page 0 is present here in the main memory. So, you can use it just like that, you do not have to swap in or swap out, it is a hit here. And the next memory reference is for page number 3, and page number 3 is not present and there is no free frame here. So, we need to choose one of 2, 0 and 1 to swap out. 0 will be used and 2 will be used and only then 1 will be used. So, 1 is the page which will not be used in the near future, which will be used after the longest amount of time, and 1 is chosen for replacement and 1 is moved out and 3 is brought into the main memory. And the next reference is for page number 0. 0 is present here already. So, there is no need for replacement, you can use 0 as such. And the next is for page number 4 of 2, 0 and 3, say 2 will be used, 3 will be used and only then 0 will be used, and hence you can remove 0 and bring in this 4 into the main memory. And the next reference is to page 2, it is already present in main memory. To page 3 next, page 3 is also already present. Then you have 0. To bring in 0, there is no free frame here, it is not present in the main memory. Also there is no free frame here. So, you need to choose one among this 2, 4 and 3. So, 3 will be used, then 2 will be used and 4 is not going to be used. So, 4 is the one that is chosen for replacement, 4 is moved out and 0 is brought into that place. And the next reference is to 3. 3 is a hit, it is already present in main memory. Then the reference is to 2. 2 is also present in the main memory. Then you have a reference to 1. 1 is not present and you do not have a free frame. So, of 2, 0 and 3, 2 will be referred to, then 0 will be referred to and 3 is not going to be referred to. So, 3 is removed and 1 is brought into the main memory. So, you have 2, 0 and 1. Then you have page 2, reference to page 2. Page 2 is already present in the main memory and hence no problem. Then you have reference to page 0. Page 0 is also present in the main memory. Page 1 is also present. Then page 7 is not here, there is no free frame. So, you need to choose one of 2, 0 and 1 to bring this 7 inside. 2, 0 and 1 of 2, 0 and 1, 0 will be referred to, 1 will be referred to and only then this 2 is referred to and hence 2 is removed and 7 is brought in. And for the next reference 0, it is a hit, it is present in memory. For the next reference 1, it is also present in memory. So, here you can see that the number of page faults in this case is 6, 9. There are totally 9 number of page faults in optimal page replacement algorithm, whereas for the same string we saw that in the case of first in first out page replacement algorithm, the number of page faults is 15. So, here we see that the number of page faults have reduced a lot in the case of optimal page replacement. But the problem with this optimal page replacement is that it is difficult to implement. That is, it is very similar to the problem that we faced in shortest job first CPU scheduling algorithm. Here in optimal algorithm, you need to know what will happen in future, or you need to know which will be the page references that will be made in future, which is not possible or which is very difficult to know beforehand, and hence practically implementing optimal page replacement algorithm becomes difficult, but it is used for comparative purposes. That is, you try to find out what will be the number of page faults if it is optimal page replacement algorithm, and then you can devise your own algorithm and find out how many number of page faults are found or got in your algorithm, and then you compare whether your algorithm is performing much better than optimal, or is it equal to or nearly equal to the performance of optimal, and so on. So, for comparison purposes, for research purposes, this optimal algorithm is used. And then they came up with another algorithm called the least recently used algorithm. So, this algorithm is very similar to the optimal algorithm. In optimal algorithm, you look at what will happen in the future, you need to know what will happen in the future. Here you need to, or you find out what had happened in the past. So, this is an approximation to the optimal page replacement algorithm. Because optimal algorithm is not feasible, they come up with this LRU algorithm. So, in the case of FIFO, it uses the time when a page was brought into memory. Optimal algorithm, it uses the time when the page will be used in future. This LRU algorithm looks at the recent past, and it looks at the recent past as an approximation of the near future. That is, the pages have been referred to in this pattern in the recent past. So, maybe it is the way it will be referred to in the near future. So, if a page was referred to in the recent past, you assume that it will also be used in the near future, and hence you do not choose that page for replacement. So, the page that will be chosen for replacement will be the page which was not used in the recent past, or you replace the page that has not been used for the longest period of time. So, for implementing this least recently used algorithm, you associate with each page the time of last use. So, that is, whenever a page is being referred to, then the time at which that particular page was referred to is noted along with that particular page. And from that you can understand which page has not been used for a long amount of time, and the page that has not been used for the longest period of time is chosen for replacement. So, when you are comparing this to the optimal page replacement algorithm, you find that in this case you are looking backward in time, that is, you look at what happened in the past, but in the optimal algorithm you have to look forward in time, that is, you need to look at what will happen in the future. So, we will see how this LRU page replacement algorithm works. Look at this example string 701 etc. And again, here also we assume that there are 3 number of page frames. So, 7 can be brought in directly because you have a free frame, then 0 is brought in, there is again a free frame, and then you have 1, a reference to 1 can also be brought in. Now, when there is a reference to 2, you look that there is no free frame here, and 2 is also not present in the main memory already. So, you need to choose a page, you know only the past. So, you need to choose the page that was not referred to recently. So, now when compared to this particular position, you see that 1 was referred, and before that 0 was referred, and before that 7 was referred. So, because 7 was the page that was not recently used, then that page is chosen for replacement. So, 7 is chosen for replacement, 7 is removed and 2 is brought into the free frame. And the next reference is to frame number 0. So, frame number 0 is already present, so it is used, and at this time the use of the frame at this particular point, that is, though 0 was brought in earlier, it has been referred to now at this particular time. So, this time is also noted for this page number 0. And then the reference is to page number 3. Page number 3 is not present here, and hence you need to choose a page for replacement because there is no free frame as well. So, which page is chosen for replacement? Here 0 was used before this and 2 was used before this and 1 was used before that. So, you see that the one that was not recently used is 1. So, 1 is chosen for replacement. So, here you need to be careful that though 0 was brought in earlier than 1, the 0 was brought into memory much earlier than this page 1, it was used recently, and hence 0 is not chosen for replacement. 1 is the page that is chosen for replacement because that was not referred to recently. So, 3 is brought in and 1 is swapped out. So, 203 is now in main memory. And the next reference is to page number 0. So, you see that 0 is already present, there is again a reference to that. So, the time of use alone is updated. And then you have a reference to page number 4. You need to bring in 4 is not present in the main memory and you have no free frame. So, you choose the one which was not used recently. So, before reference to 4, 0 was used, 3 was used and only before that 2 was used, and 2 is chosen for replacement is removed and 4 is brought in. So, 403. Then there is a reference to 2, 2 is not in memory and there is no free frame as well, and hence you need to choose one to remove outside. So, 4 was used, 0 was used and only before that 3 was used. So, 3 is chosen and 2 is brought inside. And the next reference is to page number 3, and page number 3 is not inside, no free frame. So, check which was used earlier. So, 2 was used and before that 4 was used and only before that 0 was used, and hence 0 is chosen for replacement. So, you remove 0 and 3 is brought inside. So, 4, 3 and 2. The next reference is to page 0. The recently used was 3 and before that 2 was used, and 4 is the least recently used and hence 4 is chosen and 0 is brought inside. You have 0, 3 and 2. And next there is a reference to 3, it is a hit. For 2, it is a hit. For 1, then again you need to choose a page for replacement. The least recently used is 0 because 2 was used, 3 was used and only before that 0 was used. So, 0 is the least recently used page and 0 is removed and 1 is brought in. And then a reference to 2, it is a hit. Then a reference to 0, not in memory, there is no free frame. Hence, you need to choose one that was not recently used. So, 2 was used, 1 was used and only before that 3 was used, and hence 3 is removed and 0 is brought inside. And a reference to 1, it is a hit. For reference to 7, choose the least recently used. Between 1, 0 and 2, 2 is the least recently used. So, 2 is removed, 7 is brought inside. For 0, it is a hit. For 1, it is a hit. So, here you see that there are 12 number of page faults. So, compared to FIFO which had 15 page faults, this is less in the for LRU, but compared to optimal which had only 9 page faults, this is more number of page faults. But this page replacement algorithm or this least recently used page replacement algorithm was found to be a very good page replacement algorithm, and it is used very often. And how do you implement this least recently used page replacement algorithm? You need hardware support for implementing LRU, because you need to find or determine the order of use based on the time of last use. So, you have two methods in which you can implement this LRU page replacement algorithm. One is the counter method and the other is the stack method. So, we will see how each of these methods is being used for implementing LRU. For implementing this counter method, for every page entry, you also have a time of use field. You maintain an entry in the page table for every page. So, along with the entry for every page, for each page in the page table, you have an additional field which is called the time of use field, and to the CPU you add a counter. So, whenever there is a memory reference that is made by the CPU, this counter value is incremented, and whenever a page is referred, the counter value is copied on to the time of use field for that particular page. So, if page 1 is referred to, then immediately you look at the CPU's counter value, and that counter value will be copied onto the time of use field in the page table entry. So, when you need to replace a page, you will pick the page which has got the least value of this time of use. So, whichever page was recently referred to, that page will have a higher counter value, because the counter is being incremented regularly. Whenever memory reference is made, the counter is incremented in the CPU. So, the page which has got the maximum value will be the one which was referred to recently. So, you need to check, or you need to look for the page which has got the least value for this time of use field. So, when you are doing this kind of looking for this the page with the least time of use value, you need to search the page table, and that requires some amount of time. And another thing, another overhead that you have in this implementation is that you need to write to the memory for each memory access. That is, whenever there is a memory access to a particular page, you need to update the time of use field. So, where is this time of use field present? It is present along with the page table entry, and the page table is kept in memory, and hence each and every time you update the time of use field, you will update the page table entry in the page table entry which is kept in memory. And another problem that you can face here is that there can be an overflow of the clock. That is, the clock is, or the counter is maintained as the clock is maintained as a counter. That is, you keep on incrementing each and every time a memory reference is made. So, what can be the maximum value of the clock? So, how you cannot go on incrementing to infinity. So, the overflow of the clock has to be checked, and the times must be maintained when the page tables are changed. Suppose you are removing a process because of CPU scheduling, and you are bringing in another process, then the page tables will also have to be changed for that particular process, and accordingly the times have to be maintained properly. So, the next kind of implementation is the stack implementation. In stack implementation, what is done is, a stack of page numbers is maintained in a doubly linked list. So, whenever a page is referred to, whenever there is a reference to a particular page, that page is moved to the top of the stack, and hence you can find that the bottom of the stack will have the least recently used page. But the problem here is that because it is maintained as a doubly linked list, and if you are trying to remove some page from the middle of the list, and you say there is a reference to a page which is in the middle of the list, you may have to remove that page, and you may have to bring it to the beginning or move it to the top of the stack. There you need to change pointers, the forward pointer, the backward pointer, and then adding here also you need to change the pointers, and hence you need to change nearly 6 pointers while you are moving the page from one place to another. But the advantage is that you do not need to go do a search for replacing a page, because when you are trying to replace a page, you try to remove a page which is present in the bottom. The bottommost page is the least recently used, and hence no search for replacement is needed. So, just see a diagram in which shows how you use a stack to record the most recent page references. This stack that is shown here is a stack at this particular time before A. Before A, whichever is in the top is the recently used, 2 was used, and before that 1 was used, and before that 0 was used, and before that 7 was used, and before that 4 was used. So, this is the situation at this particular instance, and when there is a reference to 7, you have to move this page reference, page number from this particular place into the top of the stack. So, 7 is removed from here and it is moved to the top of the stack, and the other ones just go down. So, here it will look like 7 was used, and before that 2 was used, and before that 1 was used, and before that 0 was used, and before that 4 was used. So, this maintains this least recently used concept, and you can see that the bottommost of the stack 4 is the one that is least recently used. So, whenever there is a need for page replacement, the page that will be chosen for replacement will be this page which is in the bottommost stack. The advantage with this LRU algorithm is that it does not suffer from Beladi's anomaly. So, this LRU algorithm falls in a category of algorithms called the stack algorithm. The set of pages in memory for n pages will always be a subset of the set of pages in memory for n plus 1 pages. Because it is least recently used, the last recently used n number of pages will be kept in n. So, if you have n plus 1 frames, one more frame, it will be the last n plus 1 recently used frames. So, what you have in n will can certainly be a subset of what you will have in n plus 1 number of frames. So, this does not suffer from Beladi's anomaly. So, now summarizing whatever we have learnt in today's class, we learnt what page replacement is. That is, whenever there is a need for a page, that page is brought into the main memory in the case of demand paging, and if you do not have place in the main memory, then you need to go for page replacement. You need to choose one victim frame and bring that outside and bring the required page inside, and there are many ways in which you do that. We learnt how you do in optimal page replacement. You replace the page that will not be used for the longest amount of time, but this problem with this optimal page replacement is that you cannot implement it practically, and then you have least recently used. So, in this you look at a page which was not used recently or in the near past, and you look for a page which was not used recently, and hence choose that page for replacement. References, acknowledgement. Thank you.